So last time we looked at right. So what we showed is that in general, U is C1 alpha. These are uniformly elliptic. And second is that if F is concave, then U is C2 alpha. Right? Now it doesn't matter whether it's concave or convex. This is a little point that I want to make, because if F is concave, we can go back to the convex one by taking F tilde to be F tilde to be minus of F of I. It doesn't change ellipticity, it just inverts the concavity to convexity, right? Because if there are minuses both ways, so the cone of monotonicity is not affected by this. Right? So, and how the argument went? The argument was that, so you look at the diameter of the image, right? And then you cover it with two scalar balls. One was cover this image, which is the image of value of V1. Well, the image is irrelevant, right? After this step, and then first you cover it with epsilon balls, and then what you are able to do is that when you cover this with epsilon balls, what you are able to do is that on a good set, A is a good measure like epsilon to the minus n square, U E along some pure second derivatives is Hessian separates from the supremum by a factor which is minus some gamma, right? I mean, you can take it to be 1/4. Okay. So what did we do? Every time the diameter is bigger than half, so this is like almost of the order of half of this, and this happens on a set of good measures, right? And you know that the pure second derivatives are subsolutions, which is where you use this concavity property of F. So then, what does the Digiotti's lemma tell you? That in half the set, it has to separate uniformly. So therefore, this implies that UEE is less than equal to supremum minus some gamma in B. This gamma that you get is what you. So this gamma that you get, you now cover with order gamma balls. And because the pure second derivative separates, right, by an order gamma, so the gamma ball, so suppose this is the gamma ball which contains the supremum of UEE, that particular U, then that gamma ball will not be present in half the covering. Okay, so you can get rid. So then, you have covered by one less gamma ball. And this gamma is kind of more universal, depends on ellipticity, dimension, and nothing else, right? And the concavity character, thanks to the concavity character. And then again, as we half. Okay, so half the ball is covered by one less gamma ball. Now again, you argue similarly, if diameter of d square of u of b half is bigger than half, then if diameter of b half is bigger than half, then again it will imply that d square u, the 1/2 square, is covered by another less gamma ball or by two less gamma ball. So there is an intermediate step over here where you have to rescale it and go back to the previous situation. Okay, but that is solved. So in this process, if you keep continuing, what you see is that at some finite number of steps, which is of the order of gamma to the minus epsilon square or epsilon 4, gamma to the minus n square or n to the power 4, you will run out of all the gamma balls. So at some point, k0, which is entirely decided by these universal constant considerations, you have to have that. So therefore, at some k0, diameter of k0 less than half. And so that means that at a universal scale, you get that the oscillation has decreased by half, right? And then if you iterate this, what you get is d square u is c alpha. And once t square u is C alpha, then you know that any directional derivative solves the following problem. And then if you apply this order theory, you first get that ue is equal alpha because this coefficient matrix now is in C alpha. So u is in C3 alpha because this happens for every directional derivative. And so this matrix is C1 alpha, right? So UE becomes C3 alpha, so U becomes C4 alpha, so you can keep continuing. So you can go all the way up to St. Philip. Okay? And so this kind of a thing also works in boundary value problems. So, and this I need because I will eventually do Monge-Ampere where such things would come up. So even in the boundary, this kind of an estimate is true, a priori estimate is true. And that is a consequence of boundary Harnack inequalities that I have done. So what is the strategy of arguing? Now first I assume that I'm dealing with a flat space. Okay, if you do things in a flat space and then by some compactness arguments that Hirsch will show, you can, and then I will just be looking at translation invariant situations, and then by compactness arguments that Hirsch will show in this last lecture perhaps, you can cover variable coefficients or like smooth perturbations of that. Okay, I mean that is kind of the shorter theory. So the prototypical case is that I have, you know that these directional derivatives solve. So UE, if you call it Z, it solves Aij, Uij, this linearized thing, right? Bij equals to 0, the one over 0. So what I want to do is that I want to analyze the derivatives in flat domains first. Okay, so I look at Uij, Bij equals to 0, and then I will go back to U. And then what I have, what I take is that B equals to say 0 on xn equals to 0. Okay, so this is the xn derivative. In a flat boundary, of course, when you sort of flatten things, you capture variable sort of there are variable perturbations of it, but then they are handled by compactness arguments of the kind that Hirsch would at least allude to later. Okay, so the hard thing is to understand what happens in the most homogeneous setting, which is this. Okay, so of course there is a coefficient here which is unavoidable, which is the two derivative of. So I have a domain which is say C2 or plus. If I sort of move it, I get something which is of this kind, which takes into account the second derivative. Well, there is also a so this is the first derivative, and then there is this Ui equals to 0. Okay, but I will just ignore these first order perturbations. Okay, so this captures the second derivative of the transformation, which I will ignore. Because I just want to give you ideas how you sort of proceed with this theory to get the boundary version of it. So, and what I want to emphasize now is that the boundary version is rather soft compared to the interior case. Why? Because once you have this, by a very standard argument, because there is an affine function, it's a plane, right, which is below. You can use a constant times xn as the barrier function, right, in this domain, and you can show that mod b is less than equal to constant times xn. And in fact, this argument works for more general domains with XTD and wall condition, but here you can use affine functions as barriers, right? So once you have this, and then you know that xn is also a solution to this, right? And so therefore, if I apply the boundary Harnack, if you remember in yesterday's lecture, I said that if I have V by U, I don't need the sign of V, provided I know that V by U is bounded. Because finally I am able to trap it between Vk and Ak, and I apply the boundary Harnack to positive functions, which are Vk of U minus B, or V minus Ak of right? So this is what I apply my boundary Harnack to and compare it with that. So, but in this case, in the case of Lipschitz domain, you don't have an a priori whether V by U is bounded, which is where you need to start with assuming that both are non-negative, which is where you can show that they vanish at the same way. But in this case, this is available for free because I know that if I have a solution to a non-divergence equation, V has to separate like the distance. Okay, so therefore V by xn is bounded, and now if and xn is also a solution to this non-divergence equation, and this is one good feature of a non-divergence PD. Affine functions are annihilators, or affine functions are in the kernel of the operator, and so therefore, if I apply the boundary Harnack to V, I get that this is C alpha, and therefore you get that V is C1 alpha. And now how do I go back? So now if I deal with a fully nonlinear equation in a flat boundary, when I use a transformation, I will capture X. But all I'm trying to say is that if you know how to understand this problem, then you can sort of handle small perturbation of it. which will be decided by the regularity of this transformation, which is the regularity of this graph coordinate for the domain. Okay. So once you have this, so I will just analyze the translation invariant situation. What is here? Here, what you do is that you now derivate in the tangential direction. Okay. If you derivate in the tangential direction, what do you get? So if you derivate in any of the xi direction or ei direction, where I is between 1 to n minus 1. So this is xn. Then what you get is that Lf is by u by Lij of well, that means the uk. So let me call it uk and k between 1 and uk and u is the 0 here. So if u is 0, all the tangential derivatives are also 0, right? This is all justified by standard sort of a difference quotient type argument, okay? Because the difference quotient, like the derivative, solves the same PDE, okay? So instead of uk, if you are very pedantic, you should be using u of x plus hek of x. It's the same, okay? So this is what happens. And now this uk fits into this paradigm. This uk is like my v. So what I get is that uk is in C1 alpha, right? So this will tell me that first, what do I know? So I know that all the ukj are in C alpha for k equals to 1 to n minus 1 and j equals to 1 to n, right? And now I know that this whole Hessian, so what is my starting point? This whole Hessian has to lie in the zeros of this operator. So therefore, by using the equation, I get a bound on the UNL. So I get that these are in C alpha, and because they have to respect the PD, f of b square u equals to 0, so UNN cannot be very wide, right? So therefore, if I use the equation now, then I get that UNN is also in C alpha. So this is the general description of how you. So of course, the ellipticity comes into play in a very major way. So this is the general description how you get C2 alpha. As like in the interior, if you know that at the boundary C2 alpha, then you can keep bootstrapping. Okay. So there is a C2 alpha. So the C2 alpha theory at the boundary, if you see, I am not using convexity anywhere. Because at the boundary, you have a better regularity. So what does the Krylov-Safanov theory tell at the inside? The solutions are no better than C alpha except for dimension 2. But the boundary Harnack inequality is telling you that this is better. U is C1 alpha, right? For Aij, Uij equals to 0 with just the uniformly elliptic coefficients. So at the boundary, the C2 alpha theory does not need the concavity, but the interior theory requires the concavity or convexity. But if you put in all the two, you get that the most general result that if I have f of u x, you can even put du and all the cosmetic terms inside. 0 because f can be put in here, and u equals to g. So this is in omega. This is on the boundary of omega, and f is concave and elliptic. So if you assume this to be ck alpha and the boundary values to be ck alpha, k bigger than equal to 2, then what you get is that the solution u is in ck alpha as well. Okay. So you have a boundary estimate, you have an interior estimate, and a priori, assuming that the solutions are classical, and then you run your method of continuity, okay, to solve boundary value problems. And then once you are able to solve the boundary value problems in the right way, that translates into regularity for any solution of that sort. Okay. So this is like the general theory. So once, so if you have a concave operator, then this is what you have. But near the boundary, you have regularity without the concavity assumption. And that was properly put into place. I mean, formalized in a better way, I would say, in a more recent paper of Silvestre and Silakov. But that uses some other ingredient, which is a Sabine's flatness feather. So I will not allude to that because the center point of the symposium is around the ideas of Luis Caffarelli. So this is one thing. So this is one general description. So this would not be needed now, but it will be needed when we do the Monge-Pierre theory. Okay. So now the other thing is that if you see the original proof of this Evans-Krylov, it's quite heavy, right? It uses like 2 scale covering arguments. Now there is a more recent argument of Caffarelli-Silvestre around 2009 or so, but they get rid of both these covering arguments. Of course, the principal tools are the same: ellipse and estimate, and the fact that if you have like along the levels, the positive part and the negative part of the matrix are all comparable to one another. So the essential ingredients are the same, but it bypasses this kind of a covering argument. And this is of very significant importance when you deal with integral differential PDs, where Luis Caffarelli has, along with Luis Silvestre, have gotten some very important results. Non-local ABP, deriving Krylov theory, which is stable as s goes to 1, and so on. So S being integral differential operators means they are non-local operators modeled on the fractional Laplacian. So this kind of an argument that they have, this alternate proof of Evans and Krylov that I will discuss right now, which is a simplification by Caffarelli and Silvestre, that I think is one of the center points of their more general work for integral differential operators. Of course, there are many other things in the non-local context, but they get a non-local version of Evans-Krylov theorem. So that is a paper around the same time. So I just want to describe that how these ideas fed into this local context gives a much elementary proof of this. Well, elementary doesn't make it easy. I mean, it's very clever, but it is what it is. Okay. So let me just get into the details of it, and then after that I will wrap up this and go to the classical obstacle problem. So this is a very little idea, so I will not want to make this a big point. But I just wanted to do that in view of the fact that we spent a lot of time on Evans-Krylov. So what we do is the following. So instead of concave, I will assume for this proof F to be convex. Okay. Then what I will have is that, and I will also assume that I want to get the Helder estimate near 0, near origin. So what I'll assume is that d square of u0 equals to 0 and f of 0 is 0. I mean, it has to be because this can easily be achieved by subtracting f of that minus f of the d square u at 0. Okay, it doesn't change the ellipticity or the character, convexity character, nothing. This is just obtained by an easy subtraction. So what you do is that you define f tilde. Otherwise, if you don't want to assume this, you define f tilde to be f minus f of. So d square u0, what you can do is that in the very first place, this can also be achieved. What you do is that you subtract from the Taylor part here, and then you put that difference in the. So if you have this, so you can do further change. The further change would be f tilde will be f of dot minus d square u of 0. That also doesn't change. Okay, you just subtract this one. So many things can be achieved. So it's a two-step process, but you can assume that d square u of 0 is 0. I mean, it's not even needed, and it's not even sort of put as a reduction in their paper. But I just want to make the whole argument as simple as possible. Okay, d square u of 0 and f of 0 is of course 0 because d square u has to lie on the zeros of f. Okay, so f is convex. So then, if I replace the concavity there by convexity, what I will have is that the pure second derivatives are super solutions. So this is the replacement, right, in the whole condition. So now here is the argument. So for a given V, which is a subset of Rn and a fine variety, so what you do is that you define U of xv Laplacian over V of U. And you do this for all affine varieties in Rn, translated at x, okay, all affine subspaces. And now here is my lemma. So I will assume that all my second derivatives are bounded by 1. So in particular, the Laplacian is also bounded by 1. Okay. So now I show the following lemma, and this is all that you require. That if for all V in Rn, one has that U. So I should not call it UXV because U is used here. So let me call it W. Okay. Because it's otherwise very confusing. Okay. So W of XV is bigger than equal to -1, that is trapped from below by -1, okay, in V1, then I want to say then there exists theta universal, theta bigger than 0, that is all that I need. Only depends on ellipticity and convexity character, such that W of XV is bigger than equal to -1 plus theta for all V in subspaces of Rn and all X in V half. This is the point. So you are able to push up the minimum. Okay, you are able to push up the minimum, and that again is kind of the fact that you cannot have a wild convexity character, right, for a super solution. Because otherwise, if this theta, so what can happen is that if this is -1, and if this theta is too close to this, then the function has to sort of come like this, right? So that means that super solution is not going to have this property. And each of this W for any V is a super solution. Why? Because it's the sum of pure second derivatives which are affine independent that lies in this V, right? Because this is the Laplacian along V, and Laplacian is the sum of all pure second derivatives. So each of this, so is it clear? Each of these are super solutions. Okay. So how do I prove it? So the proof is quite geometric. So what you assume is that we want to quantify this theta. So the proof is like as follows. So suppose this is -1, and if this theta is very small, okay, so I'll just exaggerate the picture. This is my 0. So suppose not. So then there exists some x0 in B half and of variety in Rn such that W of x0 B0 is less than equal to -1 plus theta. Finally, I will quantify this theta. So let me just sort of have that this theta is, I don't know, maybe somewhere over here, right? This is my theta. So then I know the following. So now what I do is that I do the same thing as I did for my subsolution estimate. This theta may appear very small, very skinny. But then the thing is that if I take a different power of theta, then this whole thing can get enlarged. Okay? So this is what I will do, and then I will sort of shift the whole thing. So what I do is that, so therefore I look at W plus 1. This is again a super solution, right? So W plus 1, so W plus 1 is well, so my W of x0 is somewhere over here, okay? So then what I do is that I flip this picture around this theta. So what I do is that, well, I don't flip it at present. So if this is theta, no, in this proof I would not flip it. If this is theta, I mean to say that if I rescale it to 1, which is to say that if I do flipping in, this becomes 1. But then the region, if I have a distance which is like theta to the half, this is, if I zoom in by theta, then this distance is much larger, which is to say that if I take W plus 1 by theta, this is the value over here, and then I look at the set where this is bigger than theta to the -half. Right? Which is to say that I want to look at the region where W can cross theta by 2. So I should write it better. This is -1 plus theta. This is -1 plus. Sorry, so this is what I meant. So just move it a little bit, and then this is 1. So this is also very skinny, very tiny compared to 1. Okay, but then compared to this theta, this is a big number, right? If I take the ratio. So this quantity bigger than theta to the -half is the same as asking that W should be bigger than -1 plus theta to the half. But this is very small. But then here I can use the L-epsilon estimate. What do I know? I know the value at x0, right? I know the value at x0. At x0 the value drops a lot, right? I know that for this function, so let's call it v of x0 equals to is less than equal to 1 by this condition, right? Because this difference I have scaled it to 1, and W is somewhere here, and so therefore this value is less than equal to 1. I mean, the worst case scenario is that it is at this theta. Theta means -1 plus theta. Okay, but this is all that it can happen, right? I mean, there is nothing more dramatic than this. So this happens, and then and what do I know about V? So this V is a super solution. So I should use a different notation because this V is very bad because this V is also the variety. So H. So H of x0 is less than equal to 1, and H is a super solution. So then if the infimum is small, then there is an L-epsilon estimate, right? So therefore, the set where H is bigger than, this quantity is bigger than theta to the -half, intersection d1 by 4 less than equal to theta to epsilon by 2, right? So it's a very small region where it becomes so large, right? Therefore, going back to the original situation, what I have is that this W is less than -1 plus theta 1 by 2. The values of W is less than this because there is a small region where it can escape this. Because if I make this 1, this side, if I make this 1, it's like theta to the -half, and so that is a very large number, right? So you cannot have that if W of x naught is here, it has to bend down too much to come there. This looks small, but if I sort of magnify this theta to 1, this starts looking like a very narrow spike, right? And that cannot happen. So this happens in a set omega in B1 by 4, such that the complement of it has very small measure, such that omega minus, sorry, the other way. B1 by 4 minus omega has measured less than theta to the epsilon by 2, right? And now what do? Now I'm in a very good shape. Now I have to use somewhere the fact that they're all zeros of this operator, right? So now I have to use the following fact, that I know that since f of d square u equals to 0, it would imply that d square u plus is comparable to d square u minus, right? Okay, and so in particular this implies that the trace, because all norms you can take that they're all equivalent, right? So you can take the trace norm here and the trace norm here, they all have to be equivalent. So trace of d square u plus is comparable to the trace of d square u. And now what do I know about W? So I know that this W, which is W of x comma v naught, which is this v naught, suppose not there exists this v naught, W of x plus v naught is less than equal to -1 plus theta half, right? So let me draw another picture. So now I forget about the theta and focus on theta half. Okay, so I'm not now I've sort of gotten rid of this. So theta half is not very big either, right? So this theta half is over here. So this is -1 plus theta half. This is -1, and my 0 is far away. Okay, very very far away. I mean, if you want to make this picture like this. So therefore, the other thing is that I know that the trace of d square u minus is bigger than equal to -1, and W of x v naught is bigger than equal is less than equal to -1 plus theta half, right? So therefore, you see that the difference, which is trace of d square u minus plus trace of u d squared minus plus W of plus or minus e. So trace of I'm sorry. Trace of d squared u minus is bigger, less than equal to 1, because u minus is like the minus of the negative part. Okay. The case of because u so d squared u is what? D squared u is equal to d squared u plus d squared u minus. Okay. So I've just written it the wrong way. I'm sorry. So trace of d square u minus is also less than equal to 1 because I am assuming that the Hessian is bounded. I already have C11 estimate. Okay, and this I know. So then what can I tell? What I can tell in that case is that plus W of x naught v naught is less than equal to theta to the half. Okay. So because what is telling is that W of x naught v naught is kind of so W of x of v naught, and this is for all x in omega. Where is omega? So on this set, the exceptional set has very small measures. So this information happens for all x in omega, which is in B1 by 4. Okay. So on a large set in B1 by 4, this happens. So if you see that W of xv is somewhere here, the trace of d square u minus can go at most to this. Okay. So therefore the gap is very small, which is theta to the half. Right. And now what can I do? I know that trace of d square plus minus trace of d square u minus will be equal to W of x v naught plus W of x v naught complement. And now I want to get an estimate on this term, okay, which is over here. So what do? So I now move this term to the other side. So, well, I'll just write out what I mean. So trace of d square u plus minus w of x p naught orthogonal complement is equal to trace of d square minus plus w of x p naught. And this quantity is very small. It's like theta to the half, right? This quantity is at most theta to the half. So that means that this quantity over here is also very small. So this difference is also at most theta to the half. Okay? And at the same time, I know that d square u minus has to be at least comparable to minus 1. Because trace of d square u minus or trace of d square u minus at least has to be comparable to 1. Or minus of trace of d square u minus has to be comparable to minus 1 because it has to lie below w of x p naught. Because trace of d square u minus dominates minus of w of x p naught, right? Because it's the negative part of the matrix, right? So therefore so this is the region. So this is the region where minus of trace square u d minus lives. It is very below. And I know that the trace of d square u plus and the trace of d square u minus are comparable, right? So therefore, this will tell me that if the trace of d square u is also comparable to plus 1, right? Because trace of d square u minus is comparable to plus 1. Why? Because it lives in this cell. So minus 1 plus theta half is like at least 1 by 2, right? In size. And therefore, I know that the difference between trace of d square u plus and this is very small in theta. So if I adjust my theta appropriately so that theta half is very small, I can say that this is also a good positive chunk, right? Because if the difference is small, this is good enough. This is a good positive number. So this also has to be sufficiently positive. So what I get is that over this set omega, which is almost covering in measure P1 by 4, I have a lot of good information. So therefore, with this, what I get is that on omega, is that P1 by 4 minus omega is almost comparable to 0, which is like theta to the half. I have that W of x V naught complement is bigger than or equal to a large positive constant, which is comparable to 1. At the same time, I also know that W of 0 V naught equals to 0. Why? Because the Hessian is 0 at 0. That is normalized. So what am I having? Again, this is my familiar situation, right? Again, this is a very nice situation. I have a super solution which is 0, 0 at 0, and on a good chunk of set, it escapes C. So this is the level C. And this measure is at most like theta to the half. So it will have a very skinny region to get down to 0. And this is sort of violating the concavity property of a super solution, which is to say that the convexity cannot be too large, right? So therefore, this shows that, and this is a contradiction. And so that means that this quantifies my theta. This theta cannot be too small. So with this argument, so where is my? So this is what happens, right? And now in particular, so I need to pass on to as an intermediate step. I need to pass on to this affine varieties, and then I take the V to be Rn. Okay. And in the very first place, when I got V naught, there was no guarantee that V naught was not the whole space. But then when I sort of use my equation and the fact that the trace of d square u plus and d square v minus are comparable, I automatically get that V naught complement is non-empty. So that is also another subtle thing to note. But regardless, I mean, after having established all of this, what you get is that the Laplacian. So what you get is that if I apply it, so if I take this lemma, if I iterate, gives me that Laplacian of u is P alpha, right? And then the shorter theory gives me that d square u is P alpha. I'm not saying that, I mean, it's a significantly different argument, but it sort of exploits these affine varieties in a very second way, and it gets rid of the covering arguments, which sometimes are problematic in other global situations. So this is a beautiful argument due to Mr. Caffarelli, and with this, fully nonlinear form now is over, and now I go to another central topic. Well, it is the central topic, which I think with which Caffarelli kind of wrote into the scene, which is the classical obstacle problem. So now classical obstacle problem. Change the topic. So classical obstacle problem is about you. So you are given an obstacle. Let me first draw it like this, and then I will sort of. And then you want to minimize the area over it. Okay, with some boundary values. Assume it to be 0. So this is my obstacle. This is a hill with boundary value 0, and I want to sort of cover it, minimizing the area. Okay, so I want to cover it so that my area is minimum. So this is my obstacle side, and I want to cover it with the least surface tension or surface area. Okay, and this is my solution U. So I will be minimizing the surface area. But if I linearize such a problem, the linearization of the area functional is the Dirichlet functional. So I may just very well look at minimizing the Dirichlet energy. But let me tell you that because this is a very highly, the situation can linearize very well. So once you prove that the gradient is Helder, the theory very quickly applies to the original area problem as well. Okay. So if I want to look at the very sort of one version of it is to minimize this. Okay. And the other is to minimize this subject to the constraint that U is bigger than equal to psi and U is 0 on the boundary. Or if I linearize this, I get the minimum of square over the set U is bigger than equal to psi to 0 boundary values. But then once you prove that the basic Helder estimates are there for the gradient for this problem, then at a blow-up point you can always linearize it to the Laplacian. Okay, the minimal surface equation linearizes to the Laplacian. In fact, that is the linearization as it would be at contact points. Okay, so then the theory runs very smoothly. So the hard part is to understand the problem. So now, what can I say about this? So this is like existence, at least variationally, is very soft. So any question? So existence variationally is very soft because what you do is that you look at this like set which is U bigger than equal to psi. You want the boundary? Yeah, U is 0. Okay. So this is a convex set, right? At least in a Hilbert space, which is and this is like minimizing the distance, right, to the origin. So you have a convex set in a Hilbert space. Okay, apply any of your functional analysis lemma, the Flower-Minty lemma, that tells you that there is a unique closest point to the origin. The unique closest point to the origin is the one that minimizes this Dirichlet energy. So the variationally existence is quite easy. But if you have to prove some good structural properties of U, regularity, and then understand the contact set and so on, it becomes a somewhat more technical theory. So the history goes like in 1930s. Once and Vasilescu showed that from the date you can see that it cannot be Draghi once, showed the USCB. Okay, but then later on you can show the optimal regularity that I will come to in a while. Okay, so I'll discuss this problem in more details. So essentially what you are trying to do, either you minimize the surface area, so what you have is an elastic membrane that you load over the obstacle. So at the point where it doesn't touch, it solves the minimal surface PD. But if you linearize the problem, it solves the Laplace equation. And if you see that, I mean, this is only expected to touch at the points of these upper hills, right? Because if you touch at any of these points below, so let me move this point a bit up. Let me sort of make this in like this. You are not expected to sort of touch this over here because then you will be sort of increasing the area. But this you can formalize by a variational argument, which is what I do now. So first claim is that claim superharmonic. That follows variationally because you can only perturb the test function up. Because U is supposed to minimize the area. So if you take phi to be positive, if you look at this energy, that of U plus T phi, then you have to have that T prime of 0 is equal so E of T is bigger than equal to 0, right? Because it's only one-sided condition. You can only move it up, right? And not move down for a positive perturbation, okay? Which is say 0 far away. And then if you sort of expand this, E prime 0 bigger than equal to 0 is just telling you that grad u times grad phi is bigger than equal to 0, but that is the weak formulation for minus Laplacian of u is bigger than equal to 0 because phi is non-negative. Okay. So therefore, that sort of settles the thing that you can only touch at these upper hills, not these lower ones, the one over here. Okay. So this is one part. I don't have any order in which I'm writing one. Okay. I will do as far as I can, and then of course, I mean there will be later lectures where I do this in more detail. I will be spending around 4 lectures on this anyway, so I'll be at least presenting, giving you a good glimpse of how Caffarelli tackled this theory. Okay, so variationally, this has been looked up in the 60s by several people, Luis, Caffarelli, and others. So Banerjee, Lecture, and others. So they were able to get all the way up to optimal regularity of the solution. But then to understand how the interface is, that is where this free boundary. Why is it called the free boundary problem? That is what I need to know. So I need to introduce a few quantities. One is that if I call this set V equals to psi, this is called the coincidence set. And the boundary of the coincidence set is the free boundary. Why is it called a free boundary? Because the boundary depends on the solution. Okay. And the principal questions of interest are the following. The questions of interest. Optimal regularity of solution. The second is how regular is this interface? Is how. Okay. So now, in order to understand this first question, let us understand the simplest situation. So suppose I have a hill like this, because locally these are the points that it will touch. So I can, if I just want to concentrate on a local behavior, I can get rid of the fact that where the other touching points are. I can just focus on one hill, right? Because that is where I would capture the local properties, right? So on this hill, if you see over here on the coincidence set, that is on the set where u equals to psi, you will have that Laplacian equals to Laplacian of psi. But by the time it leaves the coincidence set, because it minimizes the Dirichlet energy, u has to be harmonic. And Laplacian equals to 0 on the set where u is bigger than psi. So the Laplacian has a discontinuity across, okay? So therefore, the optimal regularity that you can expect for the solution to have is C11. And this problem was first settled by Feshel. And then later on generalized by Banerjee and Lecture, okay? But in this particular lecture, I will give a much more geometric proof, which is due to Luis Caffarelli and also Caffarelli and alt. Okay, so I'll keep the center point as Luis Caffarelli. For the regularity of the free boundary, it's another story that I will soon build on. Okay, so this I won't even try to touch for a while. So before even trying to look at the problem of the interface, which is the boundary of the coincidence set or the free boundary, the new interesting perspective that Caffarelli brought in are these extremal operator considerations or non-variational methods, okay, which is what we dealt with in the last lecture and the beginning of this lecture. So how these extremal operator considerations are brought into play. So now, in order to understand that, let us look at the following situation. So suppose I have this hill. So I will just now focus on one hill, and I will take that the obstacle, in order to have the compatibility condition at the boundary, I will say that far away from the boundary, this obstacle is going below. Okay, so this is my obstacle side, so that I can sort of put it in this range. Okay, and this is my solution U. Okay. Now, if I take if B is a super solution, super harmonic, okay, such that is bigger than equal to psi in B1. So the problem is only stated in B1. Okay, so this is -1 to 1 and B1. Then I want to claim that B is bigger than equal to U in B1. And U is the minimizer. Because if not, then what will happen? If not, then B minus U has a negative minimum. right? And that cannot happen on the contact set, because on the contact set, V has to be bigger than equal to U. So the negative minimum for V, so V lives like this, has to happen somewhere on this point. But on this point here, U is linear, like harmonic. Of course, it's not linear, but this is a 1D picture. U is harmonic and V is subharmonic. So here U is harmonic and V is superharmonic. It's a subharmonic, right? You see, like, because the picture looks like this, the hill has to go below. So a superharmonic function, at least in 1D, cannot have this shape, right? So you see, like, this cannot be. So at an interior point, a superharmonic function cannot cross below harmonic function. Okay, so this violates, and this cannot be. So therefore, this cannot be. So this sort of puts into light that I can define the solution as in the Perron method. Okay, Perron way of approach. Which is, what I do is that I look at all possible super solutions. So I look at all V such that V is bigger than equal to psi, V is bigger than equal to psi, and V is bigger than equal to 0 on the boundary. And then I take the infimum of all such V, and this I define as my U tilde. Just by this argument, it would be too premature on my part to say that U tilde equals to U. Because it could be that there is, because in the very first place, it's not even clear that U tilde minimizes the energy, right? So I have to prove a few things, okay? So I cannot jump too much ahead of myself. So this U tilde that I define, okay? Again, the envelope of super solutions, superharmonic function. So U and V superharmonic. So the most important point that I missed. So you take the envelope of all superharmonic functions which are above the obstacle and bigger than equal to 0 on the boundary, and you take the infimum of this. So the envelope is also superharmonic, okay, U tilde. And now I want to say, which is a major claim, is that tilde is quasi-convex. Which is to say that there is this C, that is, there is this C bigger than 0, such that tilde the C mod x square. Or differently, you want to say that the pure second derivatives are bounded from below. I mean, at this point, it's not even second derivative, but that you can make sense in terms of the second order incremental quotient, which is what I will do now. So I do the following. So I draw again this picture several times. Right? And now what I do is that I look at precisely the second order incremental quotient. So I look at U tilde of x plus HEI. This has to be above psi of x plus HEI. And then I look at U tilde of x minus HEI. Again, also has to be above psi of the same value. And then what I do is that I add plus C times H square. Right? This C depends on the second derivatives of the obstacle side. Now this is bigger than equal to psi of x plus HEI. Okay? So this is bigger than equal to psi of x plus HEI. Psi of x minus HEI plus CH square. But then because psi is C2, this obstacle is C2, these second derivatives are bounded from below by if I take the C to be the bound on the second derivatives of psi, this is bigger than equal to 2 times psi of x. Right? Agree? This will be the bound because this is like the incremental quotient, second order incremental quotient. And now what I do is that I divide this whole thing by half. So I take this divided by half, and so therefore I can divide this whole thing by half. I take this sum, divide and then divide by half. And so this sum, so what I get, the upshot is therefore what you get is that U tilde of x plus HEI, U tilde of x minus HEI, CH square divided by 2 is bigger than equal to psi of x. And this is also superharmonic, right? It satisfies the constraint. So I just need to look at points which are close because far away, I know that U is harmonic. U tilde is harmonic, right? Because this obstacle separates from 0 far away from the boundary. So I know enough about U tilde far away from this obstacle, right? A simple argument shows that just outside this set, U tilde is harmonic. So this is also satisfied near the boundary. Why? Because by then the psi had already gone below 0 by a large amount. If you take h to be small, so you take h to be like smaller than this distance. Okay, this distance to the divided by 10 million or 20 million. Okay, so that you don't run into these other complications. So h is very small. Okay, so that which captures the distance that this psi has left my 0. Okay, has crossed below 0. So this is fine. But then what do I know? This quantity is also superharmonic, so it is an admissible function in this class, right? And U tilde is my infimum. So therefore, this quantity is bigger than equal to U tilde because it is the smallest one. So I'm not saying that this is bigger than equal to this, but just this implication without this. So I just forget this. And this is exactly telling you that U tilde is C quasi-convex. Of course, I mean, there is a little bit of a gap in my argument over here. So what I can do is that I can take one thing that approaches U tilde of x plus HEI. I can take another sequence in this family which approaches this. So I can have, so given epsilon bigger than 0, I can take some V epsilon that approaches this by an order epsilon. I can take another V epsilon which approaches this value by order epsilon. And then what I can do is that I can take the minimum of these two. And then I take V epsilon tilde, which is the minimum of V epsilon and V epsilon, and then finally let epsilon go to 0, right? So this is the standard thing in our business, right? You approach it by two different values and then you take the minimum of the two. Okay, so it's C quasi-convex. So if it is C quasi-convex, what does it tell you? This tells you that U plus C mod x square convex. So from this non-variational characterization, I can avoid all the technical abstractions that are there in this Evans-Krylov theory. And if you see, what is this? I'm taking the second order incremental quotient. This is exactly the same thing that you do for a concave operator. What you show is that the second order incremental quotients which approaches the pure second derivatives are subsolutions, right? And why does it happen? Why the same feature survives? Because any concave operator is also like an envelope of linear operators, right? Clear? Is the infimum of all linear operators. A concave function is an infimum of all affine functions. A convex function is a supremum of affine functions which are below that graph, right? So extremal operator considerations are kind of present in a very subtle way in all these aspects. So this is one thing, and now I want to show that U tilde equals to U. The variational solution that I get is the same as U tilde. Well, that is not very difficult either. After this, because here is the picture, right? Here is the picture. Yeah, and this is so far away from this. U tilde is harmonic, so it minimizes. Right? If I take any V in the region where U tilde doesn't touch this obstacle, it is harmonic, so it minimizes the energy. And on this part where it touches the obstacle, so this is my side. This V has to be above U tilde, right? But then what will happen? Then I use the superharmonicity, right? So then I can use the fact that this gradient function is a convex function, right? So that f of x equals to mod x square in Rn is a convex function. That is, there is a supporting hyperplane, so that the whole thing lies on the other side. So this point I take to be x naught and grad u of x. This point I take to be grad u of grad u tilde, and this point I take to be grad v. Okay, so if I write that, that becomes that grad v square is bigger than equal to grad u square. Okay, plus, so well, this corresponding point is grad v. This is not grad v square. Okay, so plus the differential here. What is the differential here? The differential is grad u, right? So 2, and then the difference between these two vectors, which is grad v minus grad u. Now this has a sign. Well, this should be u tilde. This is u tilde. Now this has a sign. Why? Because v minus u tilde is a positive perturbation of this. So this is the test function here, right? In this region, okay? And if you are so pedantic to take b minus u tilde plus, because you are only sort of focused on this region, okay? That is still a test function with a zero boundary value far away, okay? At least in a region that I am not interested in. And so in this region, what happens is that u tilde is superharmonic, so this is bigger than equal to 0, right? This is bigger than equal to 0 because u tilde is superharmonic, right? It is the infimum of superharmonic function, is superharmonic. So that tells you that any v which is above u or over the coincidence set has to have more energy than u tilde. So therefore, what you get is that this u tilde indeed minimizes the energy, okay, over all v which are bigger than equal to psi and with zero boundary values. So this u tilde is my minimum and it is quasi-convex. Now, it turns out that these problems can be approximated by penalized problems, which is, I guess, the approach of Stampaskia, Louis, and then Bredis and Kindleder have also pushed on that. Friedman and many others. Okay, so I will be leaving out many names. So with this quasi-convexity property, this is one way to show that U is C11, and that is the best that you can expect because the Laplacian has to be discontinuous by the time you leave the obstacle, right? How do you do it? Because I mean, but this I will give a formal proof, but that you can justify at the level of penalization that I would not do because I want to stay focused on the geometric theory of Luis Caffarelli. Okay, so what do I have? So I have on one hand that Laplacian of U is less than equal to 0. This is the superharmonicity condition. So then what I do is that I break it. I write it as U11 plus U22 all the way up to UNN is less than equal to 0. So that tells me that U11 is less than equal to minus of U22 all the way up to UNN. Now, these quantities by my quasi-convexity information are bounded below. So minus of this is bounded above. So all these quantities are bounded below by minus C. So this whole of minus of this is bounded by C. So U11 is bounded below by quasi-convexity and bounded above because of the superharmonicity. So and there is nothing special about U11. I can do it for any pure second derivative, right? And so therefore this automatically tells you that U is C11. But now what I will do is that I will do, and this is something that Bredis and Kindleder were able to justify at the level of penalization. But of course, the proof of the quasi-convexity is somewhat different in this. Okay, so it is more sort of analytic as opposed to this proof, which is more geometric. Okay, because the extremal operator considerations of this envelope is not present in the work of Bredis and Kindleder. So one has to differentiate the two proofs. This is really the new insight of Caffarelli. So now the thing is that I'll probably stop here and continue in the afternoon lecture because I have 5 minutes and I don't want to do the optimal regularity proof by the argument of Caffarelli in this file. So let me stop here. I will continue in the afternoon or later in the day, whenever it is.